this Simpa school, and I hope you people are having great time here at LAMS and enjoy this particular conference, Simpa school. Now we are continuing with the last lecture of Beatriz in Lahore. So she will continue her lectures after arriving to Karachi, the two. But today, this is her last lecture in LAMS Lahore. Over to you, Beatriz.
Thank you, Imran. Yes, that's true. It's our last lecture here. Well, for me, it's the last lecture here. It's a pity. It's been short. Anyway, let me continue with what I was telling you yesterday. I ended my lecture talking about the common problems in reaction networks. And today I will try to talk about one of the common problems. But first, so we need to see a few more things. So first, how would we, some strategies to understand the steady state varieties, positive steady state varieties. So for some networks, well, we have a polynomial system. And for some networks, it is possible to find a rational parameterization. Or any given value of the case, we can find a rational parameterization of the positive steady state for that particular case in terms of those case. And some parameters, for example, for our first network, this one, then the set of positive steady states for a fixed k can be written like this. So xa equals k2, k1, and there's no restriction on xv. So it will be points of the form k2 over k1 and some parameter. Same. That would be a parameterization. Let me give you a bit more complicated example. I think this would be example 4. For this network, I leave it for you to compute the steady state equations, and they will probably appear in my lecture tomorrow. But for now, I can tell you that for any value of k, we can write in terms of two parameters, x1, x2. Then the value of x3 would be given like this. In terms of x1 and 2 and x2 and the case. For the fourth variable, we don't even need the x1, x2. for given values of the case, x4 is just this. And for the last one, we have this. It's just so that you see a bit more complicated example, how they look like. And for this network, the stoichiometry classes would be given in the form we have two independent conservation laws. And the stoichiometry classes will have this form. So the network has rank 3. Yeah. Yeah, I probably made a mistake. K3. K3 divided by. Thank you for pointing that out. So this can sometimes be done, but not always. We're dealing with algebraic varieties. We have polynomials of arbitrarily high degree, not necessarily curves, not necessarily hypersurfaces, and this is not guaranteed. Or we can be dealing with 80 varieties and 300 reactions, 300 nomials, things like that. What we can always do, and it sometimes simplifies some of the computations for some of the strategies that will appear, is to use somehow what appeared in one of the lemmas yesterday, one of the lemmas that was also to prove, for you to prove in the tutorial, that said that given a mass action system, which is consistent for any positive point in Rn, you can always find a k for which this is a positive steady state. And with this idea, if you try to construct that k, you will have noticed this, but I tell you anyway. So we can always construct a map which depends on the stoichiometric matrix and the matrix of exponents. So this contains some of the structure of the network, this pair. That goes from the intersection of the kernel of the stoichiometric matrix with the positive orthant times the positive orthant over n to just this positive, well, everywhere. Want? Yep. In the fourth. So this is 1, 2,
1, 2, 3, 4, 4.
There is no x, exactly.
Can you explain it?
Yeah, this is part of my lecture tomorrow. So you mean how I arrived to it, or? This is system solving. Yeah, I don't know. Sometimes it's easier to get a parameterization, sometimes not. To be honest, I don't remember how I found this one and if it was easy, because I found it long ago. But it is, so what calls your attention is the fact that there is no x here. And yeah, well, there are techniques to decide whether this happens or not, but it's not super easy, and it is a problem. And it's it was actually already mentioned in the discussion. So this project proposal session that we had, and this is called ACR. So what I'm saying here is for fixed values of the case, the value for export at steady state is always fixed. It doesn't matter, you move around the variety, but this value is always fixed. And this will be one of the topics. Okay, any further questions with that? Maybe I should have asked. Okay. So for any network, we obtain the stoichiometric matrix, we obtain the reactance matrix, the one for the exponents. And then we can parameterize like this. So for any pair, mu, an element here, lambda, an element here, there is an injective map like this, where this, of course, so this is an vector of monomials. If you remember, this is the exponents are given by the columns. And this is notation for, so this is a vector. So this is notation for entry-wise, taking the inverse. So they are real numbers. We just take the inverse. So this is an injective map that parameterizes the set of all pairs kx where where x is a positive steady state for k. And also, so I'm saying it's parameterizing. So I say for any pair of this form, this is the image of something of this form. So if I start with some k and x such that x is a positive steady state for this fixed k, then I can recover this as mu times, this is k in terms of k times xb, and then x minus 1, same notation as there. So this is somehow a parameterization. It's not a parameterization of a positive steady state variety for a fixed k, which is what we have here, but it is a parameterization of the pairs parameter positive steady state. And it will be useful for some of the computations that will come next. This is called sometimes convex parameters. Hadamard product, yeah. Okay, so I said I will talk about one of the problems that I mentioned yesterday. And this will be the problem of multistationarity or versus monostationarity. And I say that a network admits multistationarity if there is some value of the case such that I get a variety, for instance, as the one that I got yesterday. So for some of the case, the variety looks in a way that there is some compatibility class for which there are more than one equilibrium. Then I say that the network admits multistationarity. If it does not, if for all case this never happens, then I say it is monostationarity. So I'm trying to understand enough of the variety to be able to answer this question. In some cases, we can just inspect the variety. So for instance, if we can get a parameterization, we might be able to say that already, right? Otherwise, still for this network, the set of positive steady states for fixed k will look like this. So I only have one polynomial condition. Which is this one. So this and this are not giving me positive steady states. Only this gives me positive steady states. How many? Depends on the discriminant. So the points here will be of the form K2 over K1 plus or minus this. And then some other value, provided that this is positive. For instance, if I take K1 and K3 equal 3, and I take K2 equal 5, and I did not make any mistake, my steady state variety will be two half lines. One will be here. And one would be here. And then, well, some stoichiometric compatibility classes do have more than 1 point. Not this, not this. So I didn't say, but here, again, x1 plus x2 equals d gives me compatibility classes. So this has no positive steady state. This one has, but at some point, I will intersect the two lines and then I will have to. So this way I can know. But this is also maybe not always, well, not maybe, it's for sure not guaranteed that I can do that. And there are many results in this direction to try to decide on whether a network admits multistationarity. Let me start with the so-called deficiency theory that already appeared in Stefano's lecture with a different focus. So I will say different things about it, but it's the same theorem. So for big networks, it might be complicated, but let me start. This deficiency theory that is comes from Einberg, Horn, and Jackson. And for this, I need to know what deficiency is. I think Stefana said it already, but let me recall. So the deficiency of a reaction network depends on the structure of the network. And it is a positive integer which is computed as number of complexes so number of nodes in the network that are not repeated minus L will be the number of linkage classes. This is, Stefano said this already. Linkage classes is for us connected components of the graph. So let me just write connected components. The graph minus the rank. So this is the deficiency, and remember that this is also the dimension of the stoichiometric subspace. And as Stefano mentioned in this paper about toric dynamical systems, it is proven that actually this number is the number of constraints that the parameters k need to satisfy in order to be, for steady states to be complex balance. It is also complex balance or vertex balance is the same. Yeah.
Sorry, so is it a result that this delta is always positive?
This is a very good question that I've asked myself every time that I talk about deficiency. I convinced myself at some point that it's easy to see, but maybe we can discuss it later.
Okay.
I think so.
I just don't see any like an obvious connection between number of complexes and number of connected components.
There is a connection in the sense that connected components contain as many nodes. So the number of nodes that a connected component can have is restricted by how independent they are linearly somehow. So there is a relation. I don't know how to compute it immediately.
Is the connected components of the network, right?
Of the network. Complex. Yeah. Okay. Yeah, not of the
variety. Okay.
No. Of course, this is only a structural thing. So here, this network has 3 connected components because I've made the reactions like this, but maybe you remember there was one network in the tutorial. I think it was the 6th network or something that had like 3 cycles. Those are the connected components.
I think it's easy to believe. Yeah, I was
right.
overcomplicating
There is a relation.
Yeah.
One needs to think about it a little bit. But yeah,
okay.
I think it's. Thanks for the question. That's a very good question. Actually, let me give you an example. So this is clear. If I have this network, so this network has 2 connected components. And then the deficiency here, so here M is the number of nodes, and that will be 5 because all of them are different. The number of linkage classes or connected components is 2, and then S would be the rank of the network. For the rank, I can write the stoichiometric matrix, and if I start writing it, so it has 2 rows because it only has 2 species. Then if I start first reaction, second reaction, and then with this one, this is just get 1, x1, 0. I could continue, but I can see already that this has rank 2. So this is 2. So the deficiency of this network is 5 minus 2 minus 2. 1. I hope that illustrates that.
Yeah, but is it not possible, like if we have, let's say the bottom right x2 is now x3, and then we can potentially have the rank of the matrix be 3.
Mm-hmm. Yeah.
But then that would make it
that would
not
be
positive.
deficiency 0 in this case. But I think there is a limit on how much you can do that. So it bounds itself. I cannot provide a complete
do it
answer
later,
to this
yeah.
right now, but I could, yeah, as I told you, it keeps coming to my head also. We can look at it later. I think I even have the computation somewhere. Okay, so this is for the deficiency. Now let's see some other, maybe I should not erase this. Another definition. A reaction network is weakly reversible. Well, let's start with reversible, which is easy. Reversible if all reactions are reversible by themselves. Sorry, complexes. If for any reaction of this form, then this reaction is also in the network. This is reversible. And we say it is weakly reversible if we can somehow undo any path. So maybe not directly, but for any reaction of this form, there is a path from this node to this node. So in this case, any edge would be part of a directed cycle. That's what I'm saying. So an example of this you have there. An example of this is the 6th network from the tutorial that I mentioned before. And there is a theorem about consistency for weakly reversible networks by Boras. I think I will, so tomorrow my lecture will be with slides. So I think I'll put all the complete references on a slide there, so you can have all of them. And here he proved that weakly reversible networks are always consistent So if you remember, consistent means there is some positive steady state for some k. And in fact, for those networks, there are positive steady states in all stoichiometric classes. And now if we bring in the deficiency, the deficiency's theorem tells us that if we have a reaction network which is weakly reversible, and we take it with transactions, of course. Then if the deficiency is 0, then for any value of the rate of the reaction rates, not for some, for any rate of the reaction, sorry, for any reaction rate, all stoichiometric compatibility classes have some positive steady state, but they have actually only one positive steady state. Only one. And actually, those positive steady states are locally asymptotically stable. Locally asymptotically stable. They are complex balance. And they are conjectured to be globally asymptotically stable. So we have answer about multistationarity for reaction networks which are weakly reversible and have deficiency 0. They don't admit multistationarity. That's one of the conclusions of this whole big thing. And now you can try. Say something for the third network in the tutorial, the one with the 3 linkage classes. There is another result that one can relate to this one. That is also based on the structure of the network. So here, the deficiency, well, the weakly reversibility is a property of the network, of the graph. And the deficiency also, but it has to do with what is in the nodes, because we are counting different nodes. And also the, that makes it different. But for star-like reaction networks. And by star-like, I mean I have a node, and then I have nodes coming in and out. Maybe many. And so on. Doesn't matter what is in the node, just the shape. There is precisely one positive steady state in each positive stoichiometric compatibility class. Actually, those networks are weakly reversible. Well, they are reversible, in fact. And they have deficiency 0. And you can find more about this in Feinberg's book, Foundations. That I will give a precise reference in the slides tomorrow. It's Foundations of Chemical Reaction Network Theory. So this is one possible approach. But as I said, there are many results in this direction, and there is not a result that covers all the cases, or at least easily. Another thing that we can do is consider the notion of injectivity. And the idea is the following. We have our mass action system. Then one sufficient, of course not necessary, but sufficient condition for monostationarity is that this is an injective function. If fx is different from fi, fy, for any different x and y, then there's no way that two different points in our n give fx equals 0 at the same time, right? There are no two positive steady states. Giving 0. Maybe this is too much to ask, but we can maybe ask this for stoichiometrically compatible steady states. And that would still be true. If this is injective within each stoichiometric compatibility class, then there is no multistationarity. So let me write precisely a condition that I need. Given a reaction network with mass action, well, maybe even without mass action in some cases, given a reaction network, if for any positive reaction rates and for any positive points in our N, such that this holds F does not get the same value at the 2 points. We say that the reaction network, because we are considering all positive rates, is injective with respect to S. This is what I will say from now on. So if a network is injective, then it does not admit multistationarity. This is the whole idea. Then there is a result that tells me that I will say this is, never mind. A reaction network is injective with respect to S if and only if the Jacobian of F depends on K, of course. So the Jacobian with respect to X is a variable, is non-singular with respect to S, or in other words, the kernel of the Jacobian has trivial intersection with the stoichiometric subspace. And we want this for all positive rates and for all steady states. So this was proven, I think, by Krayson and Feinberg for fully open networks. There are many references about related things, but I think they prove them for fully open networks. Fully open means we always have all variables coming in and all species coming in and getting out. So you can imagine, I think they call this like a continuously flow steer tank. So there is a tank where you're removing all the species and they all come in, they all go out. Or you can think of a cell where all proteins can get through the membrane in and out. So assuming all species can come in the system and go out the system, we call this fully open. By the way, you were asking yesterday. So for these networks, there's no conservation loss. This is one example, because the rank is n. We always have a reaction, gives you a column. We always have a reaction with 1 in the ith entry and 0 everywhere else for all I. So we have a basis of the column space for all n. So now, with this condition, what we do? Maybe I go there. Now the Jacobian, the kernel of the Jacobian intersects with S only at 0 if and only if, like for all k and x positive, like there, if and only if this matrix so this matrix has a reduced version of my mass action system where I removed linearly independent rows as yesterday, and this is what I call gamma prime. So this is only S linearly independent of the Fi's, and then I add here the linear conditions that I can get to define the stoichiometric compatibility classes. So if this matrix is non-singular, then I know that the Jacobian, the kernel of the Jacobian intersects S only at 0. So I want to know about the determinant. Of this matrix, which is n times n now. And I want to know that it is not 0 for all positive values of k and x. If this is the case, then the network is injective. This is what I'm saying. So now we can use this thing that I said before. I want to check whether a polynomial, so this gives me a polynomial of, I don't know which degree, because the degrees on the x can be anything. And I want to know that there are no positive roots in both the k's and the x. This can be easy or not, depending on the polynomial. But if I want to know for all k's and all x, I can use this parameterization too. And I can construct another matrix where this stays the same because this is just real entries, actually integer entries probably. So this is a matrix of constants coming from the conservation laws. And instead of this, I parameterize the Jacobian of this matrix as these times diagonal of mu times transpose of B times diagonal of lambda, I think to the -1. No, diagonal of lambda. Why is that? This is because I can directly plug in here. So x, what I want to do. Yeah, if I just compute the Jacobian of this matrix, this is what I want to do. If I just compute the Jacobian, I get this times a diagonal matrix with inverses of the x's. Yeah. So this is the same determinant as before. I just wrote the Jacobian in terms. Yeah, I somehow. Sorry, I'm making a mistake here. This is, I know. So this is the Jacobian of this. This is what I'm forgetting. I could not find the connection. So the Jacobian of this is this matrix. And now I can write this as this, just translating from that parameterization. Yeah, so this is a polynomial. This, yes, is a polynomial of arbitrary high degree in X. And this is actually a polynomial that is linear in each of the variables. So monomials can have arbitrary high degree, but in each of the mu's, in each of the lambdas, so mu is mu1 to mu r, as many as reactions. Lambda is lambda1 to lambda n, as many species. This is a polynomial that is linear in each of the parameters. Let me call this matrix m mu lambda. So with that parameterization there, what I'm saying here is that the set of all kx in R to the R positive times R to the N positive, such that the Jacobian, so this matrix is non-singular. This set is in correspondence with the set of all pairs mu lambda, such that now this matrix on there is not singular. So if there is no positive points kx making the singular, there will be no positive points mu lambda making the singular. So now I wonder whether there are positive roots for this other polynomial. And this other polynomial, I said, is linear in all of the variables. Just now I need to look at the intersection of the kernel. So this is the same condition. And now deciding whether this polynomial has positive roots or not is very easy. It comes just down to deciding whether this is non-zero and all terms have the same sign, because I will only be evaluating in positive things. I look at it as a polynomial in lambda. And maybe I make an example. So this is a result by Müller, Feliu. Again, you'll get the complete reference tomorrow. For example 1, our first example. Gamma, so gamma was -1, 1, 1, -1. So I can reduce it and stay only with one row, because they are both linearly dependent. Now I can obtain a matrix of conservation loss. This is a linear dependency among the rows. So the first row plus the second row equals 0. And I have the matrix with the exponents. Now I can write down that version of the Jacobian. So I have two reactions, so I need two mu's. Then it comes B transpose. And now I have two species, so I have two lambdas. And that would be the matrix M there, well, the upper part. Then I need to add the lower part here. So I have these two matrices, one on top of the other. And this gives me -μ1 lambda 1, 1. This is a matrix. And then I only want to know about this polynomial. So the determinant would be minus plus. So I have different coefficients. And I cannot say anything. And still, if you remember, the steady state variety was like this. So there was only one. So this is only telling me that this is not injective. But of course, this does not mean that it's not multistationarity. Injective is a stronger condition. But I will give you one example where this allows to decide. I'll end with that. So I think this is example 5. I consider this network. So here my gamma is this. And I can get rid of the last row because it is minus the third one. B looks like this. And a matrix of conservation laws could be this. Then if I construct this matrix, yeah, it's written there. So if I construct this matrix and I compute the determinant, I get the following polynomial. So non-zero polynomial, same sign. So it is injective. And if it is injective, and it can most have one positive steady state for each compatibility class. And I had some further examples, but I'm over time, so I'll stop here.
Yeah, thank you very much. Are there any questions from your?
Sorry, and what's the difference between these two statements? I must have missed it. Sorry.
Between these two, so here I'm saying that it does not vanish for any values of the mu and lambdas. And here I'm just saying, so what I'm using here is it will be linear in all of them. So I only need to look at the signs of the coefficients. Yeah.
Still saying its determinant must be non-zero.
I mean non-zero as a polynomial. Sorry, not vanish. So here it would be not vanish. Yeah, maybe it's ambiguous. I'm sorry. A non-zero polynomial with all coefficients having the same sign. This is what I mean.
Just out of curiosity, so we just need to check that matrix is non-singular. Why do you insist on computing the determinant? Because it's the hardest thing to do.
There might be other ways. Yeah. Actually, I decided to show you this result because this idea of checking the signs of the polynomial appears in other criteria somehow. Yeah, and I just wanted to, I don't have much time. I wanted to give you an example of what kind of techniques. So this is one of them. So this is only for injectivity. There is a criterion for multistationarity under some conditions. That's also based on signs of some polynomials, but it's more complicated and proof is very complicated also.
Okay, any other question from the audience? Okay, if this is again, let's thank the speaker. Thank you, Beatriz, for your wonderful lectures and for introducing a subject which was quite new and very new. And let me just mention one person here, Alicia Dickenstein, who is also one of the key organizer of the SIMPA school. Alicia introduced many things along with the system biology and the application of algebraic geometry with system biology. And because of it, she got the award for L'Oreal Women in Sciences Award for the year 2021 or 2022. And in any case, we are very close to the Women Day, which is International Women Day, which is of 8 March. So, and we have only one female speaker here, and the other one is Dr. Shaheen Nazir. So let us thank once again to Beatriz and also to Alicia Dickenstein for proposing this particular idea and introducing this particular concept to the community of algebraic geometry here, working here, and in this particular school. And hopefully you can expect in the next SIMPA calendar a lot more activities on similar kind of topics, because this area is really evolving in the algebraic geometry. All the things are quite new, and not even many books are known in this particular direction.
Yeah.
So thank you, Beatriz. Thank you very much. Thank you.
Thank you.
Okay, now we have a tea break or coffee break, and then we have a series of lecture by Meruna and then Gordian. Okay, thank you. Enjoy your